Okay, so on when, yes. Okay, so on Monday, remember, right after we finished the review, I started talking about calculating the average rate, the average speed, showing different intervals for the same trip can have different rates, and that we can look at overall average rates and instantaneous average rates, or instantaneous rates, things of that sort. So what I want to do is kind of revisit some of the definitions around there. In a line, the rate of change is just the slope, right? This is, how fast does y increase for every increase in x. And so the slope, as you know, is calculated just taking the differences in y's divided by the difference in x's. And of course, that's, that definition doesn't change, but I'd like to change the way that we perhaps use symbols to describe this. And I'm going to get to a form of this ratio that's going to be a lot more helpful to us when we're trying to decide what the instantaneous rate of a curve is at any particular point, rather than the rate of change in a line, which doesn't change along the line. So if I'm thinking about these as functions, and so if I, instead of put y, I put just f at x, 1 and 2, I essentially have exactly the same ratio, okay? And so instead of using y's, I'm using the function name instead of just the y value. Now, what I want to do is I want to take the difference between x1 and x2, and I want to call that delta x, okay? Delta is used to signify a difference, okay? And that's, delta is the Greek letter for D. If you speak Greek and you're reading Greek, you'll make a D sound when you see a delta in a Greek word. So we use the delta as a difference or a change. And I'm going to say that's the difference between x2 and x1. And so if I rearrange this a little bit, if I add x1 to both sides here, I can have an expression for x2 is just x1 plus delta x. So what this is going to allow me to do is write my slope in terms of x1 and delta x only. Okay, so x2 is implied here. Obviously, x2 is basically x1 plus delta x. That's my definition here. And then this is just a direct substitution. x2 minus x1 is delta x. And so I have this nice expression that says, okay, my function at x1 is subtracted from my function at x evaluated at x2, but that's the way I'm writing it. So notice I don't have any expressions now for x2. Okay, x2 is going to be less important to me, but this delta x notion of how far away from x1 am I is going to be pretty important. So what we have in a general function, we can say the average rate of change then at any place is going to be this difference ratio that I described. And so get used to seeing this expression, because this is going to be a very important expression for us. Now, this is the average rate of change, okay? It's the rate of change between 2 points, and for a line, that is the rate of change. If it's a curve, that's going to be the average rate of change, just like that example I gave on Monday where we have, a car trip that perhaps lasts 500 miles, and you're going to do that over 10 hours. Your average velocity is 50. 50. But what if you want to calculate your instantaneous rate of change? How are we going to do that? Well, what we're going to do is we're going to take a very small x, and we're going to make x smaller and smaller and smaller until we get this, this ratio, and hopefully this will come up with a value as delta x goes to 0. So obviously we can't make delta x 0 because we're dividing by 0. But if we take really, really small values of delta x, we still have a slope of a little tiny line segment that has a very definite slope. And so, so this notion of a limit here means that I'm going to go as close as I want to, but not exactly equal to 0. Okay, so I want to talk about rates of change a little bit, and maybe look at some alternate words or an increased vocabulary in describing certain things in functions. Now, we already talked about, you know, long-term behavior, short-term behavior, and things like that. I'm going to throw in a few more words that perhaps some of them are obvious and some of them won't be quite so obvious. So here we go. Okay, so we have a function, and if the function goes up, it's an increasing function. Okay? Simple enough? And if we have a function that changes, but in between two x values, here a and b, we can say it's increasing within this interval. All right, that's a fairly straightforward description. So it doesn't mean that the function is always increasing, it's just meaning that in between a and b it's increasing. Similarly, we can have a decreasing function, a function that goes down, right? And we can also make this definition in between two values that we can say it's decreasing within a and b. This is a little different than what you think about if you're climbing a mountain, right? You're going up or you're going down and you say, okay, the elevation's increasing or the elevation's decreasing. It's kind of independent of the direction you're taking. You're always oriented to going either up or down. But here, x increases from left to right. And so really what this is saying, as x is increasing in a decreasing function, as x increases, y decreases. Okay, and that's the important notion to think about. As for an increasing function, as x increases, y increases. If you go the other way around, if in an increasing function, if x decreases, y decreases. Okay, so there is a direction that we're looking at here. As x increases, what's the characteristic of the function? So we're either increasing or decreasing certain intervals, or overall for the whole function. Okay, so we have a couple more things. When we have a maximum value in a function, that's the biggest function that a function can get. But that's not necessarily the only place where we have a peak or a valley. And just think about yourself in a mountain range. You know, you have local peaks and local valleys. Just because you're on a mountain doesn't mean that's the tallest mountain in the world. And so similarly with functions, we're going to talk about local maximums and local minimums. And there really doesn't have to be a very precise definition of this. It just means that this function reaches a local maximum. That means everything that's close to it, and the vagueness about this is how close is close, everything that's close to it is less than the value of the local maximum, and everything that is around this local minimum is greater than the local minimum. So these things can happen very, very quickly. You can imagine kind of a rough surface where you have a lot of little local maximums and minimums, things like that. Or you can have a broad function like let's say a parabola that has exactly one minimum value to it. That would be a local minimum in some sense, but it's also the absolute minimum in another. So the notion of a local min and a local max just means around that point. You know, it doesn't, what it's really saying is that there may be other places that it behaves differently, but somewhere around that value of x, that's either the maximum it gets or that's the minimum it gets. Okay, so we have those two words, and we call those collectively local extrema. All right, we can't just say local minimums and maxes. If you say local extrema, what you really mean are both local mins and maxes together. Now, you can see that these things are curved, and we're going to define these things as concave. Concavity, you have a curve that can be convex or concave. We're just going to look at the concave side and decide which side of the curve is concave. And so think of your hand. You know, the palm is where it's concave, right? It's hard to stretch your hand back the other way, but normally, relaxed hand, your hand is concave towards the palm, on the palm side. So when it's curved up like this, that's concave up, and when it's curved down like this, it's concave down. So around your local maximums, you're going to have something that's concave down, and around your local minimums, you're going to have something that's concave up. Okay, so it just comes right back up. Now, there's going to be a point where the concavity changes right here, okay, where it goes from concave down to concave up, and we're going to call that a point of inflection. Okay, so an inflection point is where concavity changes. All right, so these are probably not as common words as the increasing and decreasing that I had on the previous slide, but these are going to be really important words for us to use in describing how functions behave. Okay, so when you're concave down, think about what's happening here. That means the rate of change is decreasing, right? So if my hand is straight like this, and it's describing, or actually let me draw it on the board, it'll probably be a little bit more clear. If I have a function that is increasing like this, and compare it to a function that increases like this, okay, the rate of change for this straight function, the straight line function, doesn't change. But the rate of change for this function is decreasing. So the slope is decreasing, and I'm concave down. I'm still increasing. It's still an increasing function, increases everywhere, but the rate of change is slowing down. Okay, so think of this in terms of motion as if your velocity is your rate of change, then your acceleration, whether you're slowing down or speeding up, is the rate of the velocity change, right? So when you're sitting in your car, you're going at a steady speed, you hit the gas, all of a sudden you start going faster and faster and faster. Well, you're still increasing in distance, but the rate of change is increasing. So concavity illustrates that. So when you're like this, that means it's increasing at an ever-increasing rate. So the rate of change is increasing, and when you're like this, the rate of change is decreasing. So it's possible to have either an increasing or a decreasing function where the rate of change is either increasing or decreasing. So in the four cases, here's an increasing function where the rate of change is increasing. Here's the rate of change, or here's a function that's increasing that the rate of change is decreasing. Okay, so those perhaps are a little bit straightforward. But what about this function? This function is decreasing, but the rate of decrease is slowing down. So you're saying that the rate of change is increasing at this point, right? So if you're slowing down and you start to say slow down at a slower rate, that means in effect the rate of change is increasing a bit. Similarly like this, okay, here the rate of change is decreasing, because think about positive and negative now, where we have a negative slope, so we're a decreasing function, and the slope is getting more and more steep, but it's a negative number. So remember, a high negative number is smaller than a low magnitude negative number, or 0. So here the rate of change is decreasing, the rate of change is increasing, and so this is concave up, and this is concave up. So when you're concave up, your rate of change is increasing, and when you're concave down, the rate of change is decreasing. So regardless of whether it's an increasing or decreasing function, the sign change, the concavity describes the same thing. So when it's concave up, like these two, your rate of change is decreasing. When it's concave, when it's like this, your rate of change is increasing. When you're concave down, your rate of change is decreasing. And I think I have the other one written here as well. Okay, so concavity is really telling you that. And I think probably in your gut feel you kind of know what this is talking about. So you're going to higher and higher numbers, but you're not getting there quite as fast, right? So the rate of change is slowing down. So since this is concave down, the rate of change is decreasing. So it's really important to pair those two. The fact that the function can be increasing or decreasing. These are increasing functions, these are decreasing functions. But then these two are the ones that the rate of change is increasing, and these two are the ones that the rate of change is decreasing. Do I have your head spinning yet? Okay, so let's get to limits now. Okay, so the notion of limits has to do with as x approaches a value, when we say the limit as x goes to c, what is the value of f at x? So that's the way this reads, is that our limit of the function as x goes to a certain value. Now, sometimes that's really, really easy, and sometimes that's really, really hard to figure out, and we'll kind of go through a couple examples. Okay, so this is really easy. As x goes to 2, what does x plus 3 go to? 5, right? I mean, this is fairly simple. Now, we'll discover why we can do it just by substituting. By substituting sometimes, and sometimes we can't directly substitute. But this one, that's fairly straightforward. How about this one? So f at x equals 2x. Okay, so if I take my, as my delta x goes to 0, remember this is going to give me now the instantaneous rate of change. What's the instantaneous rate of change of this ratio that I've defined? And what we have is 0 over 0, right? Because as delta x goes to 0, we get 2 times x minus 2x divided by 0. And so that's not so easy. But we know for the function 2x that has a constant rate of change, right? We know that the rate of change of this thing is the slope, which is 2. But yet, substituting 0 in for, how does delta x work doesn't really help us very much. And it turns out that most of the functions that we're trying to take derivatives of, we get this 0 over 0. So we're going to have to do some different things to determine the limits in a little bit more sophisticated fashion. Okay, so we know the slope of f at x equals 2x equals 2, but this difference ratio doesn't tell us the instantaneous rate of change of x as this delta x goes to 0. Okay, so I mentioned 2x is a linear function. Now remember back in the very first tutorial we had, that was on a Tuesday, you went over lines and equations of lines and things like that, and it probably seemed disconnected from the rest of what we were talking about because we were talking mostly about polynomial and rational functions and things like this. We're going to go back to, I'm going to send you back to section 2.3 and talk about linear models where the line is going to describe rates of change in certain functions, and so the slope is going to be defined as the rate of change. And so this is going to be more or less the same kind of thing with lines, but the terminology is going to be introducing more, what the physical meaning of what m is, the slope. Okay, so you're going to have a few of those, and there again, I'm going to concentrate it more in the tutorial than in lecture. So just in our regular form of the line, mx plus b, we have basically m is the rate of change, and of course the when x is 0, we have the y-intercept. Okay, so you're going to use this form of the slope, and it's going to be all nice and linear and all that. So we get this equation here, where if we have the slope equals the rate of change, we can find new values for our function by just multiplying both sides by this x minus 2 minus times, excuse me, I'm stumbling over this. If we multiply this this x minus, or this x2 minus x1, multiply that and bring it over here and then turn it around, we have this form here, and perhaps you'll recognize that as the point slope form of determining the equation of a line, but we're also going to be able to use this to predict other values based on getting this form like this. And so we're going to get to these things in a process called linearization, where we're going to estimate how a function changes without actually knowing values of the function, but we're going to do it based on the slope. But this is really just, that equation and this thing is really just the point slope form of the line. So the problems that you're going to have on this on Tuesday, and perhaps some homework problems, will be relating to word problems that talk about rates of change in linear situations. Okay, so we're going to go through this, the way to represent rates of change. Instead of m, we're going to call this f prime. F prime means it's the derivative of f. And what the derivative really is the function that describes the slope at that particular point. So you'll see this f at x, and for a line it's just going to be your slope, m. So you have a constant rate of change, and so the derivative is constant in this case. And we'll go back over some of those rules in a little bit and go a little bit more deeply into that. But let's go back to the limit now, and first see if we can develop some tools on why we would want to do this limit the way it is, and how can we put some meaning to it, and what can we do to calculate this. So what I'm going to do is, first we're going to have a line, and for now ignore the formulas on the top and take a look at the graph. I'm going to take an arbitrary function, that's this curve, and I'm going to take 2 points on that curve, and I'm going to draw a line through it. And the name for that kind of a line is a secant. So a secant is any line that touches a curve at 2 points. Okay? Just that simple. So we have a slope that we can define for that secant, right? The slope is just going to be what we had before, is just the change in the function divided by the change in x. So we have both of these forms. And so what we're going to do is we're going to make this delta x smaller. So in other words, I'm going to bring this point, this delta x now gets closer to x1 because my delta x is getting smaller. So as it gets smaller, okay, so you can see what happens to the slope of that secant. It's now a little bit larger for this curve. And if we take it to its logical end, to where delta x just vanishes, we get this notion of the tangent. Remember we talked about it, what a tangent was at the beginning. It's that line that touches the curve at one point where the two slopes are the same. Okay, so if we can calculate this function, we can either do it for a value or we can do it for the whole function. We'll have some value or some expression that tells us what the slope is at any particular point. And so that's the motivation of limits, is how can we get to this tangent line, and what kind of tools can we develop that will make this not go from 0 over 0 to some meaningful value for us. And so it's going to take some manipulations, and we'll have to understand some rules about limits for us to do that. Okay, so here's the definition of a limit, and I'll try not to speak too much over it because it's really more or less the formal definition of it. Not really formal definition, but it's a definition we're going to use. So we read that as the limit as x approaches a equals L. The limit of f at x as x approaches a equals L. All right, so we can make f at x as close to L as we like by taking x sufficiently close to a from either direction but not equal to a. So in other words, how far am I, what's my limit? How far can I go before I hit the wall, okay? So you can say, well, I want you to be, I bet you can't get to within, you know, an inch of it. Well, I can walk up to an inch of it. And you say, okay, then a centimeter, get up to a centimeter, and get closer and closer and closer. You know what my limit is, and we have some evidence that my limit will be, you know, that wall, but I'll never hit the wall, okay? So I get closer and closer and closer to it. And this is the important notion of a limit, is that we can take it arbitrarily close, but not exactly equal, okay? So we can define what our, you know, how close we want to get, and I'll give you an x value that puts you that close to that value. Okay, so if you have a function whose limit is 2, you say, well, come within 100th of 2, I'll give you an x value that puts me there. If you say, okay, even a smaller one, then I'll give you a different x value. So there's an x value that puts me arbitrarily close to my value of the limit. Okay, so if we're going, and some of this notation I've introduced before, where we put the little negative sign as a superscript to the right of A, that means it's the limit of f at x as x approaches A from the left. Okay, so from the negative side. So you're going this way. So starting from negative infinity, going to my value of A, what is my limit? And similarly, I can do it from the right side. If I'm going from this side, what am I approaching as I'm coming from the right? And so we can have two different notions of the limit. So I'm getting closer and closer to A from either side. And so I'm going to say that we have a limit if the limit is the same from both sides. And let me show you where this isn't the case. So if I have a function that looks like this, okay, so here's my A, and this is, you know, one value of y, and this is a different value of y. As I'm coming from the left, my limit may be here. As I'm coming from the right, I'm going to be heading towards this value, although I'll never get there, right? As close as anything, even, you know, a minuscule amount above A is going to point me in this direction. And so we say the limit as x approaches A doesn't exist because it's not the same from both sides. And that's a crucially important notion, is that to say a limit exists means that you can approach it from either side. Okay, so let's talk about some numbers. I know I have a lot of abstract notions, but what I want to do is say, okay, let's say I have a function f at x equals x squared minus x plus 2. Okay, so in this case, I'm going to approach f at x from values that start at 0.5, and I'm going to get closer and closer and closer to 1. And then I'm going to go from the other side. So I'm going to start above 1, and I'm going to get closer and closer to 1 from above. And so if I calculate those values, and here's a case where you probably don't need to write every single value. I'm going to post these notes, so if you want to fill out your notes, but you know, you can put the first and last values down only and be a little bit more efficient. You can see that both of these numbers get really, really close to 2. And if, in fact, if I put in a 1 in my function, I'm going to get a 2. So without evaluating the function at 1, I have evidence to say that as x approaches 1, they're both heading to the same number. They're both approaching 2. And so I'll say numerically that I believe that the limit of this function as x approaches 1 is 2. And so if we have the ground rule that says, okay, x can't equal 1 for some reason, that's off the table, how can I prove to you that that limit is 2? Well, you can say, well, can you get to 2.000 and have a million zeros and then a 1? Can you get to that close? Well, I can point out an x value that gets me there. Or if you say something even closer, I can get an x value that's even closer to 1 that puts me there. So in other words, there's no number that exists that I can't get to that is close to that limit where I have some value of x that puts me there without actually x equals 1. All right? Okay, so now let's look at something that's different. Okay, x squared plus 2x plus 1 over x squared minus 1. Okay, so note that if we expand this, we factor it, we have an x minus 1, or we have an x plus 1 that cancels, and so we have x plus 1 over x minus 1. So we know that x can't equal negative 1. So, of course, my question then is going to be, what does it approach? So I'm going to go from the left and the right, and here I'm going from from both sides. Okay, so here I'm just a little bit below negative 1, and I'm going close to negative 1, and here, oops, and I'm going close to negative 1, and from here I'm going to go from 1 close to negative 1, but not quite get there. So let me put in some values here. And that middle value is going to be right there. Okay, so let me evaluate. Actually, let me first graph this. You know what this graph looks like, x plus 1 over x minus 1. We have an asymptote at both, horizontal asymptote at y equals 1 because the degree of the polynomial is the same in the numerator and the denominator. We have a vertical asymptote because we know x can't equal 1, but we also know, because we've canceled this x plus 1, that this value here doesn't exist. So when I draw my curves, I have to eliminate, I have to make a hole here because I've already said x can't be negative 1, because in my original function, if I put negative 1 in there, I'll get 0 over 0. So, but look at where my limits are going to. If I calculate these values, okay, from both above and below negative 1, I'm going to get very, very close to 0. And so here's a case where my function can't be, it doesn't have a value at f at negative 1, but the limit as this function approaches negative 1 is 0. All right, so to revisit that statement that I made in the last chart, if I say that limit is 0, I can get as close as I want to 0 by having values of x that don't equal negative 1, but that are very, very close to negative 1. So I can get as close as I want to 0, as close as you can challenge me to get to 0. I'll find an x value that gets me there. But what we don't have is a value that f at x actually equals 0, because negative 1 is outside of the domain of that function. Okay, so we'll state here that the limit of this thing equals 0, even though f at negative 1 is undefined.